Hello everyone. Today I'm going to be going over how to solve the fourth problem from the Canadian Computing Challenge or CCC 2021 Senior Contest. It's called Daily Commute. Now for many of these more complicated problems, before you get into solving them, there's usually a better way to solve them than trying just to go in there and try random stuff. Generally the best steps that we should follow, and I'm going to follow in this video, is 1. Understand the problem. 2. Formulate an idea. And 3. Break down the idea into steps and code it. And test, of course. Now this is really not an intuitive problem. So basically it's like there are n subway stations. You start at station 1 and every day you need to reach station n. There are also W one-way, which is directed, walkways running amongst the station. So you can walk from station AI to BI, so you can walk from one station to another, in all of them in only 1 minute. There may be multiple walkways connecting any given pair of stations. That's not important. The subway line follows a certain route along the n stations, so it starts at station 1 and visiting each station once. So this one initially consists of S1 to Sn in that order. And there is from the middle between S2 and Sn is a permutation of the integers 2 to n. So as an example, we can look at the test case right here. It can be like 1, 4, 3, 2 when you have 4 stations. Now, the other important thing is that only one subway train runs along this route per day, so it leaves at station 1, and it takes n minutes after 6 a.m. The station will be at 6n plus 1, or in other words, is 1 minute to get to the next station. Now, this is the weird part. Over a period of d days, the subway line's route would keep changing. Now, at the start of one day, these two stations will be swapped. And then after this such change, the route will begin at station 1. This is all n stations, and it's just like, for example, if you look at the test case, it starts at 1, 4, 3, 2. Now it swaps 3 and 4, so it's really not like the third and fourth station, but it's like the one in the third spot and the fourth spot. So you switch these and it becomes 1, 4, 2, 3, as they describe in the explanation. The next part that is interesting is that the walkways stay the same. So let's say there's a walkway from 3 to 4 right here. There will still be a walkway from 3 to 4 right here, and these still both take 1 minute. 1 minute, which completely defies any like physical concept of like switching stations. First off, this doesn't even happen, but it's a fun hypothetical problem should it happen. So basically what it's asking for is that for each one of these days, which can be considered as a query, how long will be the minimum time to reach station n. Now, to formulate an idea, we should make a couple observations. Since there is only one subway train that runs along this route each day, the baseline time is the time it takes for the subway to go to station n. This means that you will always get off the subway only once. And you will never get back on the train. That's another way of saying it. Now, what we can do is we can split up this problem into two different cases. The first case, let's just draw this here. First case would be the subway. And like the second part of this would be to the walkways. Why? Because since you only get off the train once, the only way that you can speed up this time is if you get off the train and somehow there's a walkway that would go faster than actually riding the subway to the end, or to where the nth station is. Now let's tackle the walkway problem first, because we know that 1, there's an observation that the walkways never change. What we can do is that we can make an array, let's say w dist, that is the distance from each station, so starting from station 0, 1, all the way up to n, and it's the distance for using walkways, so it's the distance using walkways from station I to n. And I've said already n, the distance from walking from n to n is 0, because you don't have to walk. And if not possible, set to infinity. Which in our case we can just use a large positive value such as 10 to the power of 9. Which makes the final algorithm not consider it. I'll get into that later. Now the second part of this is a subway. Now the subway line doesn't really change that much. Initially there's like a value, and then like the distance to get to 4. Let's say we have an array called a subway line, S line, and for like the initial state right here, it would be 1, 4, 3, 2. I'm actually just going to add a dummy value right here, just so that we can have this to be 1 indexed. So like the one in the first position, second position, third position, fourth position, so these are indexes. Now the time it takes to get to anywhere is its index minus 1. This is very important, as what we notice is that when we just swap two items, all we're really doing is changing two values in terms of like the distance that needs to be traveled. Now the final distance, let's call this commutative distance, is equal to the subway distance, which is just equal to the index minus 1, plus the walkway distance, which we only have to compute once because they never change. We also know that the subway distance only changes for two stations. Like when we swapped the ones in 3 and 4, this still remained a distance of 1. Now, with this, we can get a basic algorithm. So basically what our algorithm would look like is get input, calculate walking distance, and then for each day, and then we should probably also calculate walking distance and subway distance. And then for each day, change to subway distance. And then we should also, with this, calculate the commutative distance. So this plus this equals commutative distance. And then change to S distance and commutative distance. And then find minimum of commutative distance. Now what we notice here is that because finding the minimum of commutative distance, there's generally what you would do is iterate through. But this would actually be a O of n squared algorithm. And for the limits that are proposed in this question, right here, n can go up to 200,000. And you can't do n squared with 200,000. So we need to decrease this down to O of n log n or better. Now a very simple way of doing an n log n is that we can represent commutative distance as a multiset. This way, multiset is, what properties are there of multiset is that allows duplicate entries of same item, unlike its counterpart the set, and it's always ordered, or always sorted. This allows us to do a very quick operation of just taking multiset dot begin and dereferencing this iterator to get the smallest value, and we can just return this value. Now, there's some other details that I'll iron through when we actually get to coding it, such as how we update values, which is really just deleting and reinserting, which is really the same as updating a value. Now, there's a couple other things that we should also talk through in details, specifically on how we calculate the walking distance, because we already know how to calculate the subway distance. So that's the other part of this algorithm that we should probably discuss. Now, to calculate the walking distance, we can use an algorithm called BFS, or breadth first search. Now, for example, we're going to completely ignore the subway during this part, and we're going to try to find the distance for it to go to n. So what our goal during this BFS is to fill this array called walking distance. Now, let's take the index 0 to n. 0, we're just going to put a dummy value here just because we're one indexing everything. And the distance from n to n is still 0. Now, for all of these other values, we're going to set them to infinity initially, just because we don't know if they can be accessed or not. And the reason why this works, by the way, if you were curious, is because when you're getting the smallest value, you'll never really get a number larger than n, because that's like the subway time, so that you can just set ones that cannot be walked through to the final target just to infinity, or a really large positive value, so that when you're getting the smallest value using the multiset, it will not consider that value. Now, the way that you do breadth first search is that you need two other data structures. You need a queue, which I will just iterate it like this. Let's just say this is the direction of the queue. And then you'll also need a, let's say, a Boolean array called visited. Now, initially, everything is false, and then except for the n. Now, basically, let's give ourselves a graph such as this one right here. So we have our n point right here, and we have all our other nodes. Let's just say like this. Now, since all of these are directed, let's say there is a directed edge from right here, right here, right here, right here, and right here. Now, what we can do is, because we're trying to search the ways that something can go to n, the easiest way to do this is if we reverse all these directions and see where n can go to. So let's reverse this direction, reverse this direction, reverse this direction, reverse this, and reverse this. Now we can do our algorithm. So we first start by putting n into the queue. And let's just first label all these. So let's say 1, 2, 3, 4, 5, 6, and this is actually 7. So let's put 7 in the queue. And then while the queue is not empty, we will keep running this. So while the queue is not empty, we take the first element of the queue, take that off, and so we're currently considering the element number 7. And now for every edge that you can visit through 7, so since you can visit number 2 and you can visit number 1, you check if it has been visited yet. So 1 has not yet been visited, so now you set that you're about to visit it. And you also set that you're about to visit number 2. And then you add those to the queue. 1, 2. So this way you're going like one layer by layer. And then you can also update the distances for 1 and 2. Since the distance for n is 0, the distance for 1 and 2 is actually 1, so it's 1 plus the current distance. So really this would equal to 1, this would equal to 1, no longer infinity. Now you would keep going. Now this edge doesn't work because it's going from 3 to 2, so you would just ignore that. Now how we can store these walkways is through an adjacency list, where it's basically like a dynamic array of where each edge can go. So n can go to 1, 2, 1 can go to nothing, the number 2 can go to 4, number 3 can go to 2, and then these two they'll never actually be reached, but right now 5 can go to 6. Now these are already reversed, but we'll have to reverse them when we're actually getting the input for this to work. Now we're almost about done right now. All we have to do is keep updating the distance until the queue is empty. So like you consider 1, you get nothing. You consider 2, you get 4 into the array, and then 4 you get nothing. So you would just update the distance for 4 to be 2, and everything, I mean, right here. So 4 would be visited, and then 4 would actually be like 2, and then the rest remains infinity. This way, that's how we can get a walking distance array. And just like this, we have our entire algorithm. So we're ready to go into Visual Studio Code and code the solution out. Now I'm here in Visual Studio Code with a very simple template once again. Now we're going to follow our steps just like we did before. So the first thing we should do is we should get input. So int nwd, which corresponds to the number of stations, the number of walkways, and the number of days. Now we're going to get these three inputs. Afterwards, we're going to make an adjacency list for the different stations, for the different walkways. So the way that we can do this is that we can have an array of vector ints. So vector int al, adjacent list, with n plus 1, because we're going to just one index everything for the simplicity of it. And we're also going to make an array called integer walking distance, which is the distance to walk to each of the different stations. The distance to walk to the station n from each of the stations. Sorry. Now we're going to get the input for each one of these. So what we can do is we can start a loop. So before we can get the distance for all of the places, we should probably initialize the array walking distance. So for int a equals 1, a smaller than n, smaller than or equal to n. And then, so you loop through this 8 times, and walking distance of a equals to 10 to the power of 9, which is about the integer limit, and this makes it so that the algorithm will not consider it if it's not reachable. And then finally we set the walking distance of n to equal to 0 because you're already at the location n. The next thing that you should do is you should get the input for walkways. So for int a equals 0, a smaller than w. So basically this is just looping through each of them. Now we're going to have two integers, so int from and 2. We're going to get these two. And then we're going to reverse them. So the adjacency list of 2 dot pushback from. Now this is the idea that we were talking about earlier inside OneNote, where I was saying that you should reverse them so that the breadth first search will be easier to be run. So that's why the adjacency list of the ones that are 2, you push back the from. So you're essentially just reversing each edge. Now the next thing that we should do is we should run our BFS. Now in our BFS we have two other data structures. We have our queue of integers, and we also have our Boolean array. So bool of n plus 1, and then I'm gonna do a mem set just to be safe. And now we're ready to start our BFS. But first we gotta insert a base case. So visited n equals to true, and also q dot push n. Now while the queue is not empty, we will get the first element. So let's say int cur station equals q dot front, and then remove that element, q dot pop, and then we will iterate through each of the stations that that station can visit. So we can do this through a C++11 style. So for constant int next station, I'll do camel case, station to in the range of the adjacency list of current station, we will check if that station is already visited yet. So if it is already visited, we will not continue to consider it, just because that would be very inefficient and you might run into infinite loops. So if visited, so if it's not visited of station next station, if it's not visited the next station, the distance, the walking distance of the next station equals to the walking distance of current station. Nope. Plus 1. Just because you've just gone like through another tunnel, which is a plus 1 minute movement. Whoops. Yeah, W dist, or walking distance. Now the other thing that we should do is that we should set the visited flag of next station to be equal to true, so that we don't actually add it to the queue like multiple times. And we should also push it to the queue. Now this would keep running until all of the distances have been recorded, like everything that can go to there. So we've done this part of the code. The next part of the code that we have to deal with is getting like the subway line location. So we can use the variable int subway line, which is an array, and that will store the location of where each of the subway is. And we call that the subway dist is equal to the index minus 1. Now, what we can do is that we can also at this point define the cumulative distance. Now, as we said, we can use a multiset for this of cumulative distance. And this is actually equal to subway distance plus walking distance. Now, we can next up, what we should do is we should get like the initial data of the subway, like right here. So like we've already gotten all these walking pathways. We should get the current setup of the subway. So for int a equals 0, I mean probably a equals 1. Just because we're one indexing everything. We're gonna get the input, so cn subway line of a. So we're gonna like get the input for that line right there. And then we're also just gonna calculate the distance of the cumulative distance. So we can do cdist dot insert. So we're gonna insert this current cumulative distance. Note that it really doesn't matter where it is, because it doesn't matter which station it is from or all that stuff. We're just going to insert it in there, and later on when we need to update it, we'll just remove one of the entries of that distance. So right now this would be equal to a minus 1, because a is the index, a minus 1, plus the walking distance of subway line a. Because the walking distance of subway line A, notice that subway line A holds the actual number of the station that is used to index the walking distance. Because right here, like it uses this station number, and like let's say the walkway from 1 to 2. Right here, when it's like 1 to 2, it's like this 1 to this 2, not 1 to 2 in terms of this order, which is why it's slightly confusing. Whereas these swaps, it's like the swap from position 3 to position 4. This is all inside the problem statement, but it's just a bit of a clarification for those that might be a bit confused. Now we're ready to go process each of the station swaps. So for each day is like a query. So A equals 0, A is smaller than D. And we're going to get the two stations are getting swapped. So in station 1 and station 2. And we're going to get these two stations. Now these two are being swapped. Now before we can do anything, we should probably get the old distance and remove it from the multiset so that we can add it back in later on. So we can do in station 1 old dist, let's do it like this, equals to, so it will be the current station 1 number, because this is actually referring to like the index. So like the current index, the current one that's in station 3, the current one that's in like the location 3, the -1 is the distance that it takes to get there. And you also need to plus the walking dist of subway line of station 1. This is somewhat confusing because this refers to indexes, and you can use subway line to get the actual station number. And then since walking distance is indexed by the station number, that's how you get it. And then since this is the index, you can just -1 off of it. And that works really well. You can just do the same thing for station 2, just quickly changing these numbers. Now what we're going to do is we're going to remove these two numbers from the multiset. This can be done pretty simply. All we can do is just cdist dot erase station 1 old dist, and we can do that for the same for the station 2 old distance. Now we can actually do the swap, because now we've removed the old distance. We can use the built-in swap function to swap the stations that are here. So 1, 4, 3, 2, like so the subway line array from 1, 4, 3, 2, it'll become 1, 4, 2, 3. So we can do swap subway line and then subway line Yep, and now we're right about done. Now all we have to do is insert the new distances in. So cumulative distance, insert. Now the new distance would actually equal to the station 1 minus 1, because now we've switched up the location of it. And since we've already swapped it out, we can just do w distance of subway line 1. Now this might be slightly confusing again, because this seems like the exact same thing as like the station 1 old dist, and now we're inserting the same thing. Like, why did we erase it? But since we've done a quick swap in between, this actually works out. Now basically what this is, like for the sample input, beforehand, like the subway line would be like 1, 4, would be like 1, 4, 3, 2 for like the initial state. And then afterwards, this is when it would become 1, 4, 2, 3. Now the walking distances for station 3 doesn't change. That's calculated earlier on. And the walking distance of 2 doesn't change. So when we're doing like station 1, when we're like station 1 this index, we're actually referring to the element 2 right now, instead of if referring to the element 3 earlier on. I hope this kind of makes sense. You might have to think about this for a second. So basically we're just doing like the station 2 minus 1, which is like the which is the station subway distance I meant. And then this is just the walking distance. Now this might be like the hard part to understand. The last thing that we have to do is we just have to get the smallest part of the smallest cumulative distance. Now since the multiset is always sorted, we can do this using a little C++ trick. We can dereference the begin iterator of the cumulative distance. This way, this is always returns the smallest element. And then when you dereference it, like this returns the iterator to the smallest element. And when you dereference that iterator, you actually get the small element. And I'm doing the \n character rather than doing like n line, just because this is ever slightly faster and it will be useful for questions that are this complicated. Now we've finished our question, so what we should do is we should run the test case. Usually some files like these take a little bit to compile and run, especially since I'm using like this header right here, which is quite heavy, honestly, in terms of their imports. And just like that, after a couple seconds, it has passed. Now this time seems kind of discouraging, 292 milliseconds, which is about almost like 0.3 seconds. But when you run it again, generally you get a much faster speed, I hope. Yeah, you get a much faster speed. And right now I'm also recording a video at the same time, so my computer CPU is already being eaten up a lot. But this exact same solution got 15 out of 15 on the CCC grader, and this is how I would solve the Senior 4 problem. Thank you all very much for watching this long video. I hope you enjoyed and understood the solution. Please subscribe to my channel for more solutions like this, and I hope to see you next time.